Hello, everyone. This is Lewis. We'll wait another few minutes here, let everyone get logged in. Those of you that are logged in, if one of you, well, if you could mention in the chat or the question box if you can hear me okay, that'd be wonderful. Thank you. We'll give it just another minute or two, and then we'll get started here. Okay, I'm going to go ahead and get started here. Looks like we got the bulk of the people registered, logged in, and then we'll, of course, people will trickle in as we go here. We got a smaller group here, so feel free to ask questions as we go, and we'll get we'll get going. And there's a couple different presentations I'm going to go through here. Two of which are presentations directly from Howe, which is the radiant manufacturer we work with. However, I will do my best to keep it as general as possible. I'm just using these for reference, and then I will go into some general check figures and whatnot that we like to use here at TEC that can help you evaluate jobs and estimate them a little quicker and give you a baseline to work out of and budget. So let me get my screen switched over here. And we're going to start looking at with installation techniques first. Like I said, some of these cover some more broad topics. I'm going to stick specifically to different installation techniques, and then we'll go into estimating, and then, as I mentioned, some general stuff from TEC. We work with Howe, as I mentioned. Most all the techniques that they use, other manufacturers are doing some version of, and they'll apply across all manufacturers. Let's get started here. Now we're going to look at a couple different types of installations, obviously, both wet and dry, so within a concrete slab and then applied to either the underside of a floor or the top of a floor with different products. We'll look at the pipe layout patterns, selecting where to locate manifolds, and then different things to take care of the pipe, make sure we're not getting any damage, and different ways to avoid difficulties. So once you have the heat loss, which is the key first step, we can start evaluating how to get that heat transfer from the floor or the wall or wherever you're installing this. And part of the design with a radiant system is the tube, the manifold, and then the controls that go along with it. We're going to kind of avoid the controls, at least for the first part of this presentation, and look specifically at the tubing itself and the related accessories. So when we're looking at a poured or wet installation, we're talking about the thermal mass that you're putting the tube into. There's obviously different types of cement, concrete, and depending if you're doing a slab or a suspended slab, a slab on grade, suspended slab, or an overpour, you may be using a different type of concrete, but these will pretty much apply across all of those. In addition to a wet poured mass, such as concrete, if you're using a paver system for a snow melt, for example, you may be installing the tube within the sand bed. It, again, will follow the same techniques that we're going to look at here. So as I mentioned, structural concrete slab or an overpour installation are the two most common wet installations. Sometimes concrete, especially nowadays, uses different mixtures or different fibers to keep it strong as opposed to wire mesh and rebar alone. Those will not have any effect on the PEX. You should obviously check with the manufacturer specifically, but most common PEX nowadays will have no issue working with additives to the concrete. Here's your general layout. You're going to have some form of insulation or vapor barrier on the bottom. The tube can either be applied directly to it, but it'll be somewhere in the slab with fasteners, and then your concrete will get poured over the top. Here's a better layer looking at it. As far as the insulation, we'll touch on that a bit more later, but you can use different types of tarp or rigid insulation. Now, Insulation underneath the floor is obviously first and foremost to keep the heat loss, directed towards your space. So it's very important, obviously underneath, but it's most important at the edges. And in fact, the ASHRAE's latest recommendations, as well as the new Illinois code, IECC 2015, both address minimums, is specifically relating to the borders and foundations if you're on grade. I do not believe there is a requirement for insulation throughout the whole slab, but depending on what code you're conforming to, that may be something you need to consider. These are general rules. As you can see here, R15, R10. Obviously depends on how much money you're willing to spend as well, but what type of insulation you're using. Some of the tarp type installations, CoverTech for example, that have a foil layer, those tend to have a slightly lower R value, but because they have an aluminum reflective layer, they're kind of directing the radiant heat in a different way. So it's not necessarily apples to apples. You can get a great tarp product and have a similar improvement as a standard rigid foam. So this one is just shown 2 inches of R10 underneath your slab, and most importantly, as you can see on the left here, is the edge insulation. Here's another look at it from what you'd see in a standard residential slab on grade type installation, where they're going down, looks here about 3 feet, but I think the code requires maybe 2 feet, something like that. I'll have to pull that up a bit later. All right, so when we get into fastening techniques, the one you see here is the most common. Just until you get into a large area, it's the cheapest as well. In a lot of cases, the concrete guy is putting in some sort of mesh anyways, so all you do is run the tube directly on his mesh. Depending on how thick the slab is, you can elevate it on chairs if needed. Otherwise, it can sit on the bottom of a standard 4-inch slab or whatnot. The ties that the manufacturer will provide are basically a zip tie. They're a little stronger to be able to manage the pipe, which, although it's pretty flexible, can be strong and pull in different directions as you're installing it. One especially important note when you're installing these is that if you're using the ties, you either got to make sure they're all pointing down or you're trimming them off, because otherwise you're going to have them sticking out of your slab, and then as you cut them off, make sure you grab them so they're not floating all over your pour. Now, some of the newer techniques that definitely help speed up installation time. So depending on how big your area is, you may be looking at these, or if you're doing a lot of these, they certainly help cut down time and cost. This is the probably most common one that you've probably seen or heard of, where they're just installing these foam plastic clips into the foam board. So obviously this would be assuming you're using rigid insulation underneath, and depending on the size of the pipe, you can use different sizes to install it. This is the gun that Howe uses, obviously, but most manufacturers have something similar. Some use similar staples and whatnot. A lot of manufacturers have these tools from like third-party vendors, and then they're just rebranding them. So a lot of them will use similar clips and whatnot, but some also have their proprietary options. And as you can see, you're basically just running the pipe as you would with the clip, or I'm sorry, with the nylon ties, but you're rolling it right on top of the foam, and then the concrete will just go over the top. This is a great option, as you can see here, if you're doing an overpour like this, or in a standard basement. It goes down really quick, and then you just pour right over the top. Going back real quick, as far as installing it directly on the insulation, there are also products out there that have like a dimpled insulation, where it's basically the same technique minus the staples. You're basically just winding the tube through the dimples and then basically walking over it to lock it in. Again, nice quick installation. Those foam panels do tend to be a little more expensive, but you know, when you start weighing the cost of the installation time, again, it basically depends on the scale of the project, whether it's worth it or not to go to that type of product. Here again, another clip installation on a much larger scale. This is a technique that Howe has, and some other manufacturers have basically the same thing. All it is a rail that you put down about every 3 to 5 feet, and it runs perpendicular to where you want your loops to line. And you just clip it in. This is great for larger areas. We've seen it used on like turf conditioning on larger fields. But again, it's another added cost to your installation, so something to be cognizant of. Along with the fastening techniques, one thing you have to be careful about with these is the expansion joints that they're putting into the concrete. Anytime that you're going over a pre-planned cut like this, we'd like to see it wrapped in like a sleeve. Here's just a simple slit side PE sleeve. You can get a hardware store, or most manufacturers offer it as well, obviously, because they're asking you to use it. And so anytime you go over an expansion joint, you want to make sure you're including these. If you're in the field and you're first doing the design, you obviously want to avoid running through expansion joints as much as you can. So in this case, it would have been a good idea to run the pipe parallel to the joint instead of perpendicular, so that you're not having to go through and put a sleeve on each of these. But once you do put a sleeve on these, you know, expansion and contraction through the joint is not going to bother the tube at all. It'll have a nice sleeve, and as it expands and slides around, no damage to the pipe will occur. And as you can see, that's what it looks like installed here. So you just want to make sure you're putting those on anywhere you have a pre-planned joint, or for example, here they're pouring half the slab and doing the other half later. Another example of where you want to put those. You could also, depending on the location of the joint or what you have available, you can throw a piece of PVC over it. Would do the same thing as well. And as I alluded to, you want to avoid those joints as much as possible. So when you're thinking about your layout, they're doing a nice double serpentine pattern here, which I'll touch on later, to avoid that joint. But even if you're doing parallel lines back and forth, up and down, you want to make sure you're running parallel to the joints if possible. Here's just another look at that. All right, so just real quick, touching on suspended slabs or floating slabs, we do get a lot of questions as far as how is the tube affecting the structural integrity of the slab, especially if it's load-bearing and suspended. It's something you do want to make the structural engineer aware of, obviously, that you're going to be running tube through it. But as you can see from this picture, it's basically the diameter of one piece of rebar. So as long as they're accounting for it, it's not causing a major change to your design at all. Once you make the structural engineers aware of it, usually it usually will not change your design at all. But it is something you want to make sure they're aware of, obviously. You do want to install the pipe at the midpoint in the slab if you can, depending on if you're going to be insulating the bottom or if you're going to allow it to penetrate the top and bottom, which you may do with a heating and cooling application. Might depend where you can put it in the slab. Also, the structural engineer might tell you, hey, I can only put it at a certain area. When you get to these more complex situations, you want to touch base with the manufacturer and see if they have a specific recommendation. But normally, all it'd be your standard installation techniques. Here they're using the nylon ties, obviously. You can also do it with wire. They have wire guns now that do basically the same technique as the ties, but will give you just a quicker installation time. Again, straightforward installation, but something you want to touch base with the manufacturer if you start getting into complicated situations like that. And as I said, we're looking at a very small percentage of the concrete displaced. Here's a quick calculation that shows it at 0.8% for a 3/4 inch pipe, which you probably will not see any thicker unless you're doing a larger field area. So once you got the pipe down, which is obviously the extent of the radiant or the mechanical contractor in most cases, you're going to have concrete guys and other trades running in all over it. So you want to take some consideration to make sure that they're not damaging your pipe. Ideally, you want to keep it under pressure, as we'll talk about a bit later. But as you can see here, as far as concrete, just have them throw down some wood boards or some other material to run wheelbarrows over and whatnot. The pipe is extremely resistant to damage. Most PEX are. This specifically in this picture is the PEX A. So it's got 80+% cross-linking. It's very, very durable and hard to beat up. And if it kinks, you can unkink it with a blowtorch or a heat gun, preferably. But again, we'll get to some of that later. Just make sure that you're coordinating correctly with the other trades and making them aware of considerations they need to take as far as not damaging your installation. Here is another suspended slab, and you just want to make sure if you're rubbing up against any surfaces like that, go ahead and either move it or put a PE sleeve on it, as I mentioned earlier, or even a piece of scrap PVC is fine as well, just to keep everything away from it until the slab goes in over it. As I mentioned, you can also do this on a wood floor with an overpour, and if you may, in this situation, you're probably not going to be putting insulation between the tubing and the subfloor. So in that case, you can either lay down some mesh and tie to that and let it sit on the subfloor, or as you can see here, they've used staples on the bottom and then a clip type on the top. Again, the staple's pretty universal. This clip on the top is basically a pipe clamp, but depending on what manufacturer you're working with, they'll have something, some similar option here, or you can, go off on your own and do standard staples and whatnot. You just want to make sure you're not compressing the tube with the staples. As you can see here, with a standard overpour material such as gypsum, you want to make sure you're covering at least 3/4 inches over the top. So here with a 1/2 inch tube OD, and then, the OD of a 1/2 inch tube plus 3/4, you're looking at 1.5 inches total, which is a pretty small area small thickness. So you can really get these into a lot of different applications if you need to. One other thing to note here on the bottom, they've actually installed some sleepers here because of the type of flooring that they're putting over it. Definitely something you want to consider, and we'll touch base on that as well. When you're doing an overpour, if the house is new construction, one of the greatest things you can do to make it easy for yourself and all the trades coming after is to have them put a double base plate in. And so, for example, these are in the picture. We have a 2x4 wall. So you would do a 2x6 double plate, and that gives, if they're putting in carpet or some other flooring, that gives them a little nailing strip at the edges of all the walls. So definitely makes installation a lot easier. If you're doing this in an existing house that they're adding radiant to, you obviously do not have this luxury. So what you can do is go and put in a small piece along the border manually, or you can just go without it. It all depends on what kind of flooring you're putting over it in this case. This is just a pneumatic stapler version of what we were looking at a bit ago for installing on a wood subfloor. Obviously, you can see it's set up to so you can stand up. Definitely makes installation a lot faster. If it's something you're doing regularly, with the subfloor installation is definitely something I would consider for speed and efficiency there. Here's just another view, standard installation, this time with clips. This is Howe's rail fix, but like I said, most manufacturers have a track similar to this. Continuing specifically with the suspended wood floors, you want to make sure that you're insulating in the cavity below the floor. Even though you're installing the tube on the top, it's very important to drive that heat up. When you're doing a suspended floor like this, you have less thermal mass. Definitely better thermal mass when you're using an overpour concrete like this versus some of the dry methods that we'll talk about, but you still want to make sure you're insulating everywhere to drive that heat up and keep your system nice and efficient, keep your heat transfer up, keep the floor warm longer so it's not kicking on and off. All right, so here, this is after they've got everything set. The concrete guy is in here and laying down his overpour. Quick note here at the top, you want to make sure that if you're not putting anything over the subfloor, that the concrete guy is spraying it with a sealer first, so that when they're pouring this, the wood's not absorbing the water too quickly and pulling it out of the concrete. Here they've put down a barrier below, as I mentioned, so that they don't have to worry about spraying it with anything. Just make sure you're coordinating with the concrete guy as far as whose responsibility is taking what, or if you're submitting a bid to an owner or a GC, make sure that everyone's coordinating who's responsible for what portions, and then you can relay that to the vendor and to your other subcontractors if needed, directing them who's including what with their proposals. As I mentioned briefly, when you're doing an over pour like this, depending on if you need to be able to nail wood floors to it or whatnot, you may need to include sleepers. So here they've gone through, laid them out every 12 inches or so, and then ran the tubing on either side. I probably would have put these a little closer together in the middle here, just so you have even spacing throughout, but just a quick reference picture here. So just a quick wrap up here of the over pour especially, but applies to slab on grade as well. Keep in mind insulation and your work surface underneath. Depending on what fastener you decide to use, which, as I alluded to, really depends on what your sub base is, and then how big the area is, how much and what tools you have available to you. And then just planning and coordinating with the other trades is so key here. Too many times, these are really simple installations when you break it down. All you're doing, on a basic slab in a basement, for example, is throwing the tube down with the nylon ties, and then the concrete guys coming after. So you just, as long as everything is coordinated out ahead of time, it makes your life a lot easier. As I mentioned, there's a couple different layout patterns you can address. In most cases, you're going to be using a standard serpentine where you're just going back and forth. When you get into larger jobs, we'll look at some of the other designs here, but this is just your standard serpentine where you're going down one way, wrapping around and back. And depending on, here's a better picture of it for you guys. Just standard wrap back and forth, back and forth. Now here you can see they've put an L shape into it. That is so that what they're doing is they're bringing the hottest water to the outside wall and around the corner, and then they're working their way back to the center of the room. So something to keep in mind, depending on where your manifold is located, if you can help it, you can drive the warmest water first out of the manifold to the outside walls or to under windows, and then work your way back into the center of the room. You can also decrease your spacing along the walls and then increase it in the middle, depending on how big the area is and how big the project is. Sometimes the designers will do that intentionally. Otherwise, the installers can do it manually on smaller jobs just as they're putting it in to help give some better heat transfer and drive the load towards the biggest heat loss areas. So here, they're doing a combination of a serpentine pattern that they're calling a double U-bend, where they're basically running loops inside each other. And what this does is it cuts down on the bend radius at the ends. Most of the time, depending on the diameter tube you're using, the bend radius does not come into play. But if you're using smaller spacing, such as 6-inch, which we'll touch on when we're doing estimating, depending on the diameter of the pipe, it can get a little tedious to have someone hold it down while someone puts on some clips or nylon ties and then bring it back. So what they've done here is you're running one loop inside the other, and then you don't have to worry about the bend radius as much except for that inside loop. Here you can see they've just conformed it to the outside wall. I mean, as you can see, this is not really rocket science. All you're doing is looping back and forth and then going back towards your manifold. As long as you keep it simple and plan out ahead of time, you're really not going to run into too many issues with the radiant system. All right, sorry, my drawing wasn't coming up here. Let's look at this other one here. So this is what they call a counterflow spiral, and basically what they're doing is they're running along the outside edge with the warm water, looping in all the way to the center, and then it's working its way back out the same way it came. This definitely takes a lot longer to install. It's a lot more planning. As you can see here, they're using the dimpled insulation that I mentioned earlier where the tube just clicks into it. That's obviously a nice speed advantage for this type of system. Howe, I don't know if I have a picture in it here. I can show it to you at the end. Has a new technique where the tube is actually wrapped in a Velcro, and then you stick a Velcro mat down that serves basically as your under garment or under layer there, and then the tube, as you roll it out, just sticks to it. So if you're going to do a complex design like this, it's another great technique. That this dimpled insulation also works well here. The counterfall spiral, the time you really want to apply something like this is when you have a big open area. It allows for a very, very even heat distribution, and you really only have the one bend right here in the middle. So while it's a little more labor intensive in terms of the design and getting it all planned out ahead of time, once you're actually laying the tube, it goes down quite a bit faster. So more planning at a time, quicker installation, sorry. And here's an example of an airport over in Germany. I believe it's in Germany. I have it tagged somewhere. Anyways, it makes it a lot easier just to do square areas at a time. And depending on the area, you can see they'll switch from serpentine to the counterflow to go around different objects and whatnot. A lot of times these will get picked up in the drawings, but a lot of times they won't. As you can see, these couple boxes going down the middle here. And all they've done is brought the tube to either side of it. So nothing, no crazy redesign of the whole system. You just, bring a couple loops around the outside there. Here's a combination of your serpentine and your counterflow. As I mentioned earlier, if you could bring the outside or the hottest water to the outside wall, that's the most ideal. And then you can work your way inwards and then either switch to a counterflow or really depends on where your manifold is located in this small of an area, but this is just an example. When you get into bigger areas, that's where the counterflow and worrying about the differences in spacing come into play. Here's the combination I just mentioned. All right, now we're going to quickly switch over to some of the different dry installation techniques. As you can see here in the bottom picture, they're showing basically a heat transfer plate attached to the bottom of the floor and then some insulation behind it. So we'll show a couple different examples. This is another thing where different manufacturers have different heat transfer plates, different options. You could do this without heat transfer plates, but you're really limiting the amount of heat you can drive upwards through that wood flooring and then through whatever surface you're putting on top of it if you don't use a heat transfer plate. And this is even more required, mandatory, necessary insulation with this type of technique, because you need to drive that heat up through the, as I mentioned, subfloor plus whatever you're putting on top of it. I believe the number Howe uses is you need to have at least 5 times the insulation below as the insulation value of the subfloor and the floor on top. But different manufacturers will give you different check figures there. You just want to make sure you're leaving a little air gap and then insulating below it. And here's a better cross section of it. Sorry, I should have had this up while we were talking about it. This insulation type is obviously most used in retrofit. If you're designing a new system, I would not recommend this be your basis of design. I would always recommend putting something over the top if you can. Now, that being said, if you're using a standard building technique and with a house and you want to add radiant to a smaller zone, it doesn't necessarily make sense to change your whole design to accommodate the small radiant area, maybe in, say, a couple bathrooms upstairs in addition to the standard slab in the basement. So you may end up specifying this type of design or wanting to install this type of design, and that's fine. But just make sure you're taking all of these steps we'll touch base on into account to make sure you can drive as much of that heat upwards. As you can see here, they got some, Howe has some numbers, minimum 19 R value when you're going over a heated space, and if you're in an unheated space, for example, a crawl space or whatnot, you want to have R30. As I mentioned, keep an air gap to keep that area warm and then drive that heat upwards. Air is definitely a fantastic insulator, which is what foam insulation is doing as well. But an air gap will help keep the insulation off of the heat transfer panels and drive it upwards. Here you go, just another cross section. Ideally, foil-faced insulation is best, and then leaving the air gap helps increase response time and make sure nothing's getting in the way of the plates and causing issues down the road. Here are a couple of Howe's different plates. The one you saw in the picture before is the most common. These are some more standard ones. Or as I mentioned, you can clip them in directly to the wood. Less heat transfer. It will definitely affect the amount of heat you can get out of the system, but definitely another technique that you can use depending on how much your customer is willing to spend and what's existing. This is Howe's most simple one. It just tacks up with sheet metal screws, and then you can run 2 strips through each joist space. Makes it nice and simple. Very good heat output for considering the type of insulation, and a very quick install, also considering the type of installation. I won't go too far into this specific brand, but basically it just heat transfer plates will fix to the bottom, and then they're showing here using like a rail at the end. You can use standard clips, talons, whatever, just to route it back through the joists. And then here it is assembled going out to a manifold. Again, this plate is specific to Howe, but a lot of manufacturers will have something similar. If you are ending up in a suspended slab, or sorry, suspended dry installation like this with the joist space, this is definitely the technique we would recommend. Makes it nice and neat and easy. If you already have a bunch of piping and electrical and everything run over this, or a drop ceiling perhaps, this would be a nightmare. So this may, in certain situations, like I said, it's not always going to work, but this is definitely the technique if you have the option that you want to use. Sorry, I'll try and speed this up a little bit so we can get to the other presentations. Again, this is mostly just related to Howe specific ones. Here's a finished installation with a couple different types of plates. All right. All right, we'll touch quickly on this and then we'll get over to the estimating. The next thing after you've figured out the area that you're actually going to put the tubing in, and you've got your tubing, well, as you're doing your tubing layout, the manifolds will definitely come into play, but the next big installation piece is the manifolds. And depending on if you're in residential, commercial, where you put it can obviously make a difference based on access and whatnot. But these can go, indoors, outdoors, in a, landscaping box, or in a nice, manifold cabinet with a locking door. A lot of times in a residence, we'll see basically just like a return air vent used as a cover in the back of a closet, for example, to hide the manifold. Super cheap, super easy, looks nice and clean, and quick access if needed. Here are some more commercial type installations, although you can definitely apply these to residences to make them nice and clean and neat. Regardless of the installation type or brand, you're going to want to run all your piping through PVC sleeves when it comes up out of the slab, just to protect it long term from anything rubbing. Here, as you can see, if you can keep them nice and neat and lined up with a piece of unistrut or otherwise, it definitely makes installation easier. It makes anyone that comes after you working on it a lot easier as well to diagnose. For example, if one loop seems to be leaking, it can be shut off and addressed, or if you need to change the flow to a specific area. One big thing that you want to consider when you're first doing your initial layout is the location of the manifolds. Not only where you want to put them, but where the space is going to actually allow you to put them. So quickly we'll go through here. This is with two manifolds split at the different ends of the residence versus having one large one. When you get into the larger the manifold, the more tube you have collecting at one little area. So in this case, they've taken advantage of that to put that at the entry, which is traditionally, a point of high heat loss with people coming in and out. So that allows that extra heat to kind of displace some of that extra heat loss. But in general, if this was somewhere else located in the house, that area is definitely going to see a warmer temperatures with all of the supply and returns coming from it than the rest of the house. So another thing to keep in mind there. Here you have, this is basically the same as the one we were just looking at, where they've got the manifold up by the front entrance, and then it routes out to all the different areas. Howe, like other manufacturers, will do layout drawings. We usually will always recommend waiting until the job is basically completely finished being laid out and approved and purchased before going back and doing the layout drawings, because until you have the final as-built, or not as-built drawings, but the final design drawings, these will change about 100 times. So best to wait till the very end, but these are definitely very useful, especially when you get into bigger areas. As you can see, they've split the manifolds per classroom here, and here, they split like a giant warehouse left and right. Different ways you can address manifold locations. Your biggest, when you get into commercial areas, usually the architect's going to tell you you get this little closet space, and that's what you have to deal with. So, but we can make a lot of different situations work. It's definitely going to affect your installation as far as installation technique and how you hide the manifold and it's a cabinet and whatnot. I can send this document out to you. I'll show you guys where it is on the website as well, but this is just a quick installation guide that goes step by step. We'll go through here really quickly, but preparation is definitely the most important with any of these systems. When you're actually installing them, it's very straightforward, very easy, as long as you've decided what you're going to do ahead of time. If you walk in and just start installing it, you're going to come up with some hiccups. So just make sure you're planning out as much as possible. Step one is definitely to locate the manifold, because you're going to run all the tube from here. If you're obviously putting it in a commercial space that's not fully built yet, you can build a temporary structure for it. But definitely step one is to locate the manifold and install it, and then you can start running the pipe from there. These, as you can see from the pictures, you can mount these in all different orientations to get to different spaces and put your manifold in more secretive locations as needed. I mean, it's water, it's a closed system, and you have a pump on it, so it's going to flow wherever you ask it to. Sorry, just going through some pictures. The second thing after you get the manifold set up is to get your pipe ends lined up. Here is a really nice installation. They've just taken a piece of unit strut with some quick clamps and thrown those down. Then you run your pipe through it. It solves a lot of headaches down the road, being able to keep it nice and neat like that. The next step would just be to apply the tubing. Start with the supply, connect to the manifold, and then just start running it out through your pattern and bring the return back. And here's already alluded to that. Next step is installing the actual pipe. When you get in these larger jobs, you can use an uncoiler, as they're showing here, to help you unload the pipe, which definitely makes a difference when you get in these large coils and these larger pipe diameters. Here you can see they've gone through and they've got all their ties holding the pipe together. When you're installing the pipe, the general rule is 2 to 3 feet for fasteners. Depending on what type of fastener or system you're using, that'll change a little. But in general, you're doing 2 to 3 feet. But you want to take special attention whenever there's going to be a saw cut or expansion joint. You want to make sure you're holding the pipe down below there and have your PE sleeve on if necessary. Depending on how deep the cut is, you can actually drop the tube down below the surface and cut through the insulation if you have to, and depress it a little bit. But make sure you're fastening specifically any weak points or where there's going to be any cuts. This is pretty straightforward, but you're going to avoid any toilet gaskets or other gaskets with the pipe. Here's just protective sleeving on the pipe. If you're going through joists, you want to put a little collar on it. One nice thing to have on hand if you're doing a larger job where they're going to be pouring kind of right behind you is to keep some couplings on hand. These are Howe's Everlock fittings. They can be buried within the slab. You just want to wrap them with, you know, a waterproof tape. Here they're just using electric tape, where Howe has a heat shrink sleeve route cross that you can put over them. Other manufacturers too. But as long as you wrap them up, these are approved for being installed in the slab. So usually you're not going to do this by choice. It's going to be that someone came in after the slab was done and cut through your tube, and now you got to dig it out and put a clamp on, or put a coupling on there. But something nice to have on hand if, you know, concrete guy puts a shovel through your tube or whatnot, you can repair it real quick and then keep the install going. Step 5, bring the return back to the manifold, connect it. All right, next step is the pressure test. The easiest is just to air test it. We have these quick air test kits. They have a little nipple on them. You basically put any pneumatic, you know, air pump up to it, keep it under pressure. When you're first doing your initial testing on the slab, you want to make sure it's keeping it for 10 to 20 minutes, then repressurize, make sure it's up to pressure again. Just allows the tubing and everything in the system to expand a little and get adjusted. And then once you get it up to pressure permanently, you want to maintain that test for at least 2 hours. I would also recommend keeping under pressure while you pour the slab. Not necessarily required, but definitely helpful. And in general, during the test, you want to keep it at constant temperature. If it's changing temperature, it could affect the pressure, and you might think you have a leak when you don't. But definitely, air testing is definitely the easiest. You can just stick them on the end of manifolds, even manifolds that are connected together. You want to make sure and install your air vents after you're doing your air tests, of course, or make sure they're closed. Otherwise, you'll obviously get some false leakage. Here's with a fluid test. All the Howe manifolds have drains on them, but if you're doing a custom manifold with copper, or if the manifold doesn't have a drain on it, you want to make sure installing one of those slightly upstream, and then simple flush type to get the fluid into each of the loops. You'll just isolate each of the loops, get the fluid all in there. Once it's all loaded up, you can cap it off and bring it up to pressure, and then same thing as before. You want to maintain the pressure for 2 hours once you let it normalize for expansion and temperature. And then you'll finish the install with the concrete. Make sure your pipe is all pretty before the concrete guy goes over it. Make sure there's no kinks. If you make sure you snipped all your fasteners, and you're basically complete. After you get the system all installed and everything, you want to bring the concrete slab for the first time up to temperature very slowly. You don't want to just start running a ton of hot water at 180 degrees, or you won't want it at 180 degrees anyway, but you don't want to bring it straight up to temperature right away. So when you're first warming the slab, just be careful. Check with the concrete guy on how many days you need to let it cure before you can run any water through it. Definitely will help make sure no cracking or anything occurs. And then finally, you're going to go through and balance based on what you decided. As I mentioned, these Howe ones, you can balance and isolate them individually. You could be making your manifolds custom with copper, using another manufacturer. Same basic rules apply. You want to make sure you're balancing based on what your design was, so that you're not running an absurd amount of water through some loops and not enough through others. This is just some quick what not to do's. You know, mounting your manifold incorrectly or just doing it hastily or dirty, it's just going to leave you with problems later. If you find a leak, you're going to have hard problems trying to diagnose it. It's going to look bad for your customer. Obviously, could reflect poorly on you as well. And so just if you take your time, do it nice and neat, makes everything easier when you're diagnosing issues later. Again, if you're not lining up the pipe, just makes it hard to track everything after the fact. Just some other quick notes. You can mount them upside down, so you don't need to run an extra amount of pipe like this. Don't want to be this guy. And definitely don't make your install look like this. I got a couple notes from guys that are having to take off here. I'm sorry, I'm running a little late here. We will have the slides together for you guys, or I can get them to you individually. Just send me a question or comment with your email address, and I can get that over to you. All right, let me quickly go over to estimating, and then we'll go to our quick check figures. I won't go through this one in very much depth at all because I'm going to give you some check figures that we would recommend personally, specifically for the Chicago area. Most everywhere, the installation estimating is going to be the same, just your temperatures and fluid flow rates might be slightly different depending on your load. But when you're estimating, you want to account for the pipe size and quantity, the fasteners and the type of installation you're using, the manifolds, and then if you're using an installation technique like a dry technique, such as rowel panel or joist space heating, those will obviously come into play as well. Different types of pipe diameter, obviously based on cost factors, but mostly installation technique and the load required. So in a radiant system, we can have much smaller, or sorry, a residential system for a basement, we can have a much smaller tube than a large snowmelt system outside. Half inch, even in commercial, is used almost all the time. Depending on the size of the area, you might go up to 5/8 or 3/4. If you're doing radiant heating and cooling, you need at least 5/8. I would recommend 5/8 or 3/4, but you do not want to use half inch if you're also using the system for cooling. So your layout type and whatnot will be affected by, obviously the type of project and the load required, the installation technique you've chosen to use, which is usually based on based out of necessity, based on the type of project and what type of area you're dealing with. Perimeter versus occupied areas, and then the spacing and square footage and layout of the actual pipe will follow the dimensions of the building in most cases and apply backwards. And then coil availability, obviously if you're doing something in a rush, you might have to select something based on what's available with your supplier. Go through this kind of quickly. I'm going to give you some numbers to help estimate these at the end, but your pipe to area ratios will depend on your spacing most predominantly. So they have these numbers here. I'm going to switch over to here. Basically, for a standard slab, standard load, you're going to be looking at 12-inch spacing. So it's basically 1 foot of pipe per square foot of area. So 200 square foot area, 200 feet of pipe. Pretty straightforward. We recommend 9-inch spacing for snowmelt outside. So that obviously ups the amount of pipe you need per square foot. When you're doing joist-based installation, if you have standard 16-inch joists, you're going to do 2 runs per joist space, so you're going to be looking at 8-inch spacing. And then depending on the areas or stairs or whatnot, you might go down to 4 or 6 inch spacing. This is just a quick example I can go through really quickly, but we're looking at 1,600 square foot facility they've got here. They're going to be breaking into a couple different zones, and as you see at the bottom, they're going to use 8-inch spacing for the perimeter and 12-inch for the occupied areas. Normally, you can do this manually in a small space like this while you're actually installing it. When you get into commercial spaces, the designer can do that, apply that directly into their design, but not something you might need to worry about in a smaller residential zone. You can just do a 12-inch spacing for all of them and start your outside strip closer to the perimeter than 12 inches. Oops, sorry, I overshot that. All right, so based on the spacing that they're using for the different areas, they're going to have a little more pipe than they are area. This was the long way to do it, the precise way. If you're doing a quick check figure, you can do that estimation by hand real quick. Yeah, as you can see, they're showing you the quick estimate on this side. The quick estimate's always going to get you a little oversized. With the piping, that's a good thing. You can use that area to bring the pipe back to the, they call it a tail. Depending on where the manifold's located, you're going to need a few extra feet of pipe. But just a 6% overestimation for an area is pretty good. And because of how we're spacing this, like basically in a grid, your estimations are always going to be pretty dang close. Let's see, it's already 1 o'clock, so I'll try and wrap this up here. When you're estimating your fasteners, depending on which one you're using, the manufacturer will give you a check figure. 1 piece per 18 square foot to 20 square feet for this specific track. Again, depending on which one you're using, they'll give you a different number. This many pieces for this many square feet, or this many pieces for this length of pipe. And I'll show you a quick estimator for Ray Howe's specific ones. Manifolds will depend on the number of circuits. They might also have different diameters based on the amount of flow rate that you have, so that'll be determined by your design. And then, as it alludes to here, balancing requirements, control requirements, how fancy a manifold and how fancy controls you use will definitely depend on the job. Using a pre-assembled manifold like this one has the air vents and drains on the one side, overall shutoff and temperature gauges on the other, and then each of the loops have a flow gauge and can be completely isolated. This is obviously super nice for most installations. But it is pricier. So in some cases, if you just have 1 or 2 loops and you don't want to go through the whole rigmarole of paying for or convincing your client to use a built-up manifold, you can definitely do a copper one. But if you can use an assembled manifold like this, it makes your life a lot easier. It makes the final project very nice, or final product, sorry, very nice. And it's very easy to maintain and adjust down the road. As I said, different sizes. Sorry, go through this a little faster. Depending on if you're doing one large manifold versus several smaller loads, the several smaller manifolds will reduce the tail length that I alluded to, but they are in general more expensive to have 2 manifolds instead of 1. So if you're unsure, as far as estimating, I would always lean to doing some smaller manifolds with your estimation, and then depending on where they can locate the actual manifold, or if they want to go to a smaller one, you'll be saving a few bucks and not have to worry about sending them an ad or whatnot. I'll go through some of these separately, so I'll skip through here real quick. Real quick on these, you want to make sure you're accounting for all the PVC pipe ends and the manifold connectors for both the supply and return. And depending on how your vendor sells them, that might be different, but your total counts, make sure you're doubling up for supply and return. Let's see, we'll go through here. As I mentioned, specialty installations like this, the manufacturer will give you, you give them the area and the layout, and they'll be able to generate a nice report for you. This is our Howe ROW panel estimator. And so, as you can see, this is a really nice system that puts the aluminum panels over an existing subfloor to give you some really nice heat transfer in an otherwise kind of imperfect installation, or unideal, I should say, not imperfect, not ideal installation technique. That's all estimating ray panel, so I'll cut through these real quick. Again, the manufacturer will tell you exactly, how many you need for different amount of feet. And with the ROW panel, as you can see here, it's 0.16 for the plates, and then, I'm sorry, 0.17 for the plates, and then they're using the 8-inch spacing with these plates, so it's a 0.16 multiplier for your pipe. In summary, make sure you're including the pipe, fasteners, manifolds, and then related accessories to the manifold, connectors, and whatnot. If you're using a plate or different installation technique, make sure you're including those. And then you'll add that into your pipe, pumps, expansion tanks, mixing and controls and whatnot. I didn't touch too much on controls. I'll do that in 1 second. I just want to show you guys a couple quick things before I get you out of here. Real quick on Howe's website. Try and get this to you guys real quick. They have a really nice calculator based on what type of installation you're doing. And so if you go to their website, you can, once you get in here, you can bookmark this, so you don't have to go through this whole rigmarole every time. But if you get to their resource center here and go to the Radiant Material Estimator. So I'll get this real quick. Once you do that once, it usually won't make you do it again. It's been a while since I've been here. But you can go through and, let's say you're just doing an overpour. So go to this tab, 2,000 square feet, plastic staple, you choose your installation type, choose your spacing, and then boom, spits out here. You need 2,667 feet of pipe. You need 1,300 staple clips. So real nice and easy. Lets you print it. You can do it for the different techniques, the ROW board, ROW plate. Obviously, this is specific to Howe, but definitely a quick, nice tool. And then let me cut back over here. This is more applicable to the designs that we do. If you've ever had myself or Bill Bailey or Bill Shannon help you with the layout, you'll recognize some of this. The most important thing I would like to stress when you're doing a hydronic system like this, specifically Radiant, is look at the feasibility. Sometimes a master bedroom on the far corner of the house, even if you already have a boiler system installed downstairs, it doesn't always make sense to run Radiant up there for a 50 square foot area. You might want to put an electric mat in there. But in general, you want to look at and be honest with the customer and yourself about the feasibility of it. So what does that include? Well, obviously, do you have a heat source available already, or are you going to be supplying a new one? Where is it going to be located? Do you have the utilities to go to it? Supply and return piping. Wherever you put the floor, you got to run piping to and from it. Installation options. We've touched on a lot of different techniques. As you can see in this picture to the right, they had to abandon an old steel or copper pipe radiant system, so they went and put Howe's ROW panel over the top. Depending on where you're installing it and what your options are, you might have to adapt. And that's also going to change the price. This route panel is not cheap. So as opposed to putting it in within the slab below, that would, or with a topping concrete slab, definitely would change the overall price. But depending on what you have, it may not be available. Sorry, before we go to the next slice, two quick more things. The use of the space and the output required are kind of the same here. You have to make sure that your customer understands the output available. If you put some radiant in a vestibule, for example, it's not going to have the same effect in a 50 square foot area as you know, a space heater or something tempering the air coming in and out. It'll definitely help keep the space warm, but your output is dependent on what the material that it's in can handle. So if it's in a concrete slab, your concrete can only get so hot before it's an issue, and the surface temp can, in a house, for example, can only be so hot before it becomes objectionable to people walking on it. So just more things to keep in mind, and then obviously costs. These systems are very, very low cost to run and operate over the life of their, and they last, you know, 20 plus years. Easy. I mean, the warranty on these, on installations like this, are at least 20 years. So the main cost is the upfront cost, and it can be very objectionable depending on the type of project and you know, the funding available. Going back to expectations, the type of floor covering is going to limit the amount of energy that you can get out of it. So specifically, some hardwood floors will limit not only the, you know, the R value is going to be causing an issue itself, but I'm sorry, guys, is going to be causing some insulation itself, but they can also, depending on the manufacturer, they might have a limit of how hot you can let the wood get. So in that case, you want to make sure you're installing a sensor within the slab or underneath the wood to make sure. But just another thing you have to keep in mind, depending on what you're putting over the top, it's going to limit the amount of output and comfort that you get out of it. Carpet obviously being the most, and then wood being very good insulators. If you have tile or marble or something, for example, that actually is only going to help your thermal mass. But hardwood and carpet, you definitely want to make sure that the customer knows that they're going to be getting slightly less heat out of that area. All right, so some basic guidelines that we use here pretty regularly. If you're doing a standard slab on grade or suspended slab with space heating, so think pole barn or first level of a house, something like that, 40 BTUs per square foot is a good estimating design size. If you're doing underfloor, so like a joist space heating, or if you're installing in a basement, I'm sorry, if a basement you can do warmer temperatures, you just don't need them as much, so we use 20 BTUs per square foot. But as far as the output expectations of an underfloor, like a joist-based installation, you're looking at about 22 BTUs per square foot. With the space heating, I said 40. Depending on the temperatures that the room requires, this may be able to go up to 50, but then you have to worry about the surface temperatures of the slab. If you're just doing floor warming or floor conditioning, it's not handling the main load, you're probably going to be looking at 15 to 20 BTUs per square foot. One thing I'll note on that really quick is when we're doing like a high-end residence, for example, a lot of times these houses will have multiple furnace systems in them, and then they want to install a boiler that can do this huge radiant output. But the fact is those are going to be overlapping. So either take those into account in your design of the furnaces and you know, decrease the load, or you know, decrease the output necessary for the radiant. Otherwise, you're going to have basically two redundant systems, which again, maybe that's what they want, but just make sure you're very clear with the expectations of the system. Snow melts, the limits, I mean, you can go to 250 BTUs plus, but per square foot, but then you're going to be looking at a lot of extra piping. You're going to have to go very close spacing and larger diameter to get that output. For the Chicago area, kind of as an overall figure, we use 125 BTUs per square foot. If you look at ASHRAE's guidelines, that kind of corresponds to a snow-free area of about 95%, or a partially snow-free area of about 99%, meaning for 99% of the snowfall, it'll melt all the snow, but while it's in the melting process, it might have some coverage on the surface. Anyways, that's a whole nother presentation on snowmelt that we can do, but 125 is our good estimating figure for the Chicago area. And then if you're doing something specialty, you know, turf field, tennis courts, pool decks, those will be dependent on, you know, surface temperature requirements or limits, and then what you're designing to. So anytime you get into a specialty thing, you don't necessarily want to use an estimating check figure, because you could be putting yourself into a corner if, you know, down the road it turns out to be something else. Touching on the heating and cooling source, if you're using a high temp boiler that's existing, or steam, for example, you may need a heat exchanger, or you may need a mixing valve. Over here on the right, Howe and other manufacturers as well have a bolt-on mixing system. So this has a little pump, supply pump, and then a thermostatic mixing head, checking the temperature and modulate or turning the pump on automatically based on whatever control you attach to it. So this is a manually set valve. So basically you set it in the field based on the highest temperature that would be incoming, and then you know, it'll open and it'll open itself up automatically to let the proper temperature through. Low temp heating, that's what you're going to actually be putting through the floor, but as far as the heat source, you might have some low temp sources from geothermal or ideally condensing boilers. I shouldn't say ideally, geothermal is obviously ideal as well, but condensing boiler versus a high efficiency boiler, or sorry, a high temp boiler is definitely ideal. With cooling, I mentioned briefly, the installation and estimating are all the same. The special considerations that you'll need to take are more on the control side, making sure you're not dealing with, you know, exceeding the dew point and whatnot. But they will, in general, have larger tubing and larger diameter tubing and closer spacing. And then you might have some specialty heat sources. You might have to run it off. I apologize, this keeps clicking over. You might be running, you know, a very small radiant zone off an existing water heater, or you might be using some heat recovery or reclaim from a chiller to dump some heat out onto a snowmelt area or another floor area. Some general starting points that we use here to estimate. If you're under 2,000 square feet for a radiant slab, you know, half-inch tube, 250 to 300 foot loops, and 12-inch spacing. So if we were looking at 2,000 square feet, we'd be looking at roughly 7 loops of 300 feet, which would actually work out to 2,100. So you have a little check figure there. But when you have 12-inch spacing, remember our multiplier is just 1.0. So we'd be at 2,000, and then you know, the loop length go on the high end here at 300. If you divide that out, you know, you round up to 7. So going back to it real quick, you know, over 2,000, we'd probably recommend looking at 400 foot loops of 5/8. But again, depending on how much control and how big the area is, those could change. When you're doing underfloor heating or joist space, you're looking at 8-inch typically. And then with joist space, we also recommend keeping the loops just a little shorter because you're going to have to leave a little room for tails as you're running through and back and forth through the joists. When it comes to the dry installs that we talked about, the different panels, As I mentioned, the manufacturer will have like a check figure or a guideline there, a multiplier, if you will, to tell you exactly what material you need there. With snow melts, we always start with 5/8 inch and 200-foot loops at 9-inch centers. Now, just real quick to kind of give you a background on where these came from, as we touched very briefly on earlier in estimating, you're going to be looking at, you're trying to keep your overall head loss of the pipe down based on the flow required. So once you determine your heating load, you're going to basically be able to back out the flow rate based on the fluid and whatnot. So usually if it's just water, if you have 100,000 BTUs, you're going to be looking at 10 GPM, then divide that by the number of loops. And then each of the manufacturers will have a table. You'll be able to go in and say, all right, I have half-inch pipe, I have 1 GPM, and then here's my head loss. So it's all about limiting your head loss to an acceptable factor. Obviously, the lower you keep it, the cheaper the pump that you can use. So there's obviously some balance there. All of these guidelines that I've given you here keep the loop pressure drop to about 10 feet maximum. In some cases, it could be slightly more or less, but 10 feet maximum is usually good. Per circuit, sorry, not per the whole system, but per circuit, and then you add a little for the manifold, and you're there. Now, just a final little checklist to go through when you're planning these out. As far as the radiant, you're going to be estimating the pipe, manifolds, manifold connectors, the pipe bends, and then any fasteners you need. I have the next item separate, manifold enclosures. That is something that you want to address. Make sure that everyone's on the same page there. But that is something that you can address separately depending on where the manifold ends up and how they want it to look. Like I said, with radiant, in residential especially, it's always best just to hide it in a closet and to use a cheap way of covering it up, whether it's an air vent cover or other type of cover. Using the joist space or the wall cavity that's already there definitely makes the easiest install. But we definitely have manifold cabinets available if you want them to stand off of the wall or depending on where they're located. You want to make sure you or the concrete contractor are figuring for the insulation. Make sure you've addressed your heating and cooling source. If you got a lot of small zones, you may want to consider a buffer tank. But when you get into the more complicated jobs with lots of tiny small zones or larger areas, I would definitely consider getting the vendor involved or your supplier to help you break down, what exactly you might need and if a buffer tank seems like a good idea there. You want to make sure you're including a proper expansion system. So how are you filling the system, how are you keeping air out of it, and how are you allowing for expansion are the 3 keys you want to be careful of. And finally, circulation control. We didn't touch much on this in the estimating portion of this job, but I can certainly answer questions as you have them. You just want to make sure that you're coordinating with the contractor and the owner so that they know what they're expecting. A lot of times buildings will use radiant system, as a accessory to their main heating system. So is it going to be controlled by a furnace thermostat or an air handler thermostat, or is it going to be controlled by a building automation system? Just another item you want to make sure is on the same page with the owner. I showed you briefly the different check figures and the estimator that Howe has available. Let me quickly just show you on that same web page. This was the calculator. If you go back to the resource center, you can see on the headers up here, you can get specifications, product submittals, instructions, all sorts of nice information available here. Everything is searchable, downloads with PDFs. But I mean, your suppliers will obviously be normally happy to get any of this for you if you let them know. Just a quick resource if you might be out in the field. They do have apps you can put on your phone as well. And that should about wrap us up here. I will give you our contact info. Bill Bailey and Bill Shannell are running our hydronics department. They are our main two product managers. They both have, 25 plus years experience with these systems. So they're happy to meet you out on a job if needed, or if we need to discuss different layouts. Myself, Lewis, I'm in the office most of the time. I also do these webinars occasionally, but I'm definitely available to help you, do a layout, look at a job, answer questions. And Mitch Viss is our newest addition here. He's going to be a product manager as well for some of our hydronic products and can help with different, a site visit or different applications. As you can see, we've done some various different scales of hydronics jobs in the past, so we can help with all different sizes. Over here on the right is the big dormitory for Loyola, I believe. Down on the right is just a boiler system for a church, and to the left a radiant system for a higher end residence. So we can cover all sorts of bases. And let's see, most of the questions I got here are related to emails for the different presentation materials. But if you guys have any other questions, feel free to ask now, or you're free to go. Again, my name's Lewis, and shoot me a note, and I can send you whatever you need. Otherwise, I'll hang around here to see if there's any other questions. Thank you very much for attending here today, guys. I appreciate it. Sorry, I definitely went over on time here by quite a bit, but I will have the whole thing recorded and posted on our website as well. And I think that's it. Thank you very much, guys.